Hi, have you ever wondered why airline ticket prices change so often? You might be looking at a $300 fare one moment, refresh the page, and it's jumped to $450. It feels random, even sneaky. But it's not random, it's modeling powered by deep analysis of costs, revenue, and something called break even. And what made me think, what if I tried to figure it out myself? In this presentation, I'm walking you through a real case study using Air India's Bangalore to Delhi route in March 2019, using actual ticket price data and applying concepts from our Bazaar 2020 unit. We are going to answer one core question: how many tickets does Air India need to sell to break even on a single flight? By the end of this video, you'll not only know that number, you'll also understand how airlines use profit modeling and break-even analysis to make critical pricing and route decisions every day. Let's get into it. Let's begin with the foundation. The profit model. A profit model is essentially a forecast. It estimates how much money a business can make based on how much it sells, how much it charges, and how much it spends. The formula is very simple. Profit equals to revenue minus costs. But the beauty lies in the breakdown. For an airline, revenue comes primarily from ticket sales. That's relatively straightforward. But costs, that's where it gets layered. There are two types of costs. First one is fixed costs. Fixed costs are costs such as fuel, pilot salaries, aircraft leasing, and airport usage fees. These costs don't change whether there are 10 passengers on board or 180. The second one, which is variable costs, which includes in-flight meals, luggage handling, boarding costs, and these are tied directly to the number of passengers. What I did was use real ticket price data from Air India flights in March 2019 and filtered it to just one route, Bangalore to Delhi. I converted all prices to Australian dollar using the historical exchange rate for that period, which is Indian rupees 1 equals to Australian dollar 0.0203 Australian AUD. Then I used Excel to calculate the average ticket price, and thanks to subtotal filtering, I avoided the mistake of averaging hidden or empty rows. I got the result of $342.92 average per ticket price. Now, since the data set didn't include cost data, I referred to a global airline industry reports to build a realistic assumptions. Based on the IATA's 2023 World Air Transport Statistics and Airlines for America's Passenger Airline Cost Index, I estimated fixed cost per flight equals to 8,000 Australian dollar and variable cost per passenger equals to 70 Australian dollar. These numbers reflect average operating costs for a short-haul flight using an Airbus A320, which is what typically used for this route. To be transparent, these are industry averages, not Air India's specific disclosure, but they're credible, used by analysts, and more than suitable for our model. Now that I had both revenue and cost inputs, it was time to build a model. Using Excel, I created a dynamic table that calculates the following for every possible passenger count from 0 to 180. Then, to take out the revenue by calculating the average ticket price times passengers, and then to take out the cost, I simply use the formula as fixed cost plus variable cost times passengers. And finally, to take out the profit, it is simply revenue minus cost. These three formulas form the heart of my model, allowing me to simulate what would happen if the flight was half full, nearly empty, or completely sold. I used a realistic assumption of 180 seats, which is standard for many domestic aircraft like the Airbus A320. This provided a complete picture of how performance changes across the full capacity range. I then graphed these values using line charts in Excel, plotting passenger count on the x-axis and cost and revenue on the y-axis. What this showed me very clearly was the exact point total revenue overtakes total cost. That moment is when airline goes from operating at a loss to starting to generate profit. And that moment has a name, the break-even point. What's powerful about this is that it transforms abstract numbers into something you can actually see. Instead of just trusting a formula, I can now show visually and numerically that for Air India, this break-even happens at exactly 30 passengers. It also lets me adjust inputs like ticket price, fixed cost, or variable cost, and immediately see how that shifts the break-even point. This interactivity is what makes the model not just informative, but actionable, a real decision-making tool. To show this more clearly, I created another second line chart plotting profit against passenger count. The curve starts deeply negative at 10 passengers. The flight is running at a $5,000 plus loss, but as more tickets are sold, the loss narrows steadily and then flips positive at the break-even point, where revenue begins to cover all the operating costs. From there, it accelerates rapidly. Once the flight has crossed that threshold, every additional seat sold contributes directly to profit. Because the major costs are already paid for, this is the power of covering fixed costs early. The margin per passenger becomes very high. By the time the flight reaches full capacity, the profit exceeds $40,000 AUD, which shows just how much earnings can scale beyond break even. This is why you sometimes see airlines selling last minute tickets for surprisingly low prices. It's not because the airline is desperate, it's because they've already passed the break even threshold. And at that point, even heavily discounted seats are profitable since the only cost remaining is variable, and that's far lower than the ticket price. In other words, they're monetizing empty seats that would have otherwise flown unused. I didn't stop there. I ran some what if scenarios to test the sensitivity, and I made some assumptions that what if fuel prices surge and fixed costs rises to $10,000, or what if Air India runs a sale and average fare drops to $300. In each of these pushes, the break-even point higher goes higher from 30 passengers to 37 or even 44, depending on how much costs rise or ticket prices drop. This shows how even small changes in pricing or expenses can have a big impact on whether a flight makes money or loses it. Airlines constantly adjust their prices and plan how many seats they need to sell in order to stay profitable. These what if scenarios help them prepare for different situations like fuel price changes or discount and make better decisions before a flight even takes off. This break even model makes that whole process easier to see, test, and understand. What I loved about this project was seeing how something as theoretical as break-even analysis has such a practical high-stake application. Before this, I thought airlines just price things based on demand. But now I understand that behind every ticket is a financial model that accounts for costs, margins, and thresholds. From Bazaar 2020, I took tools like profit modeling, cost analysis, forecasting, data cleansing in Excel, and used them to stimulate how a global airline might make real flight decisions. It made the subject real for me and gave me skills I could apply to any business in any industry. Thanks for watching. Next time you're on a plane or even just browsing flight deals, think about this. Someone in finance department has already calculated exactly how many people need to be in those seats for that flight to make money. And you just learned how to do it too. Yeah, thank you.